Well, hello. Back for more torture. Education. Here's chapter 7, dealing with acids and bases. Let's go into the learning objectives here. Here are the learning objectives for this chapter. Let's talk about acids and bases. So, acids, so they taste sour. And most foods are acids, to be honest with you. So, it's hard to find basic foods. Humans don't really like the bitter flavor. Bases taste bitter, but acid tastes sour. Lemons taste sour. Lots of things. Even bitter melons. I was curious about bitter melons, if they were really alkaline, and I measured them. They are, in fact, acidic. So even bitter melons are actually sour. And acids also turn litmus red. Litmus is a dye that's pH sensitive, and it turns red in acid and blue in base. And acids also react with most metals to release hydrogen gas. The ones that they don't react are things like gold, platinum, silver, those kind of metals. So they're really expensive ones. They release hydrogen gas. And you can react with a base to form water and a salt. So bases taste bitter. They turn litmus blue. They feel slippery. This is on skin. Okay, so this is true for all bases do feel slippery on skin, but actually, if something is slippery, it does not mean that it's a base. So sulfuric acid, for instance, is slippery, but it's obviously an acid. Also, oil is slippery, but it's neither an acid nor a base. And bases also react with water to form water and a salt. So you've learned something there. So acids taste sour, bases taste bitter. Well, what does salt taste like? It tastes salty, right? Something different. So salt is something completely different than acid or base. It's neither. It's lost its properties. So when acids and bases combine, they form salts, and the salt no longer has the properties of the acid or the base. So here's litmus. So you can see that if you are colorblind and can't see this, the red litmus turns blue in a basic solution, basic or alkaline solution, and blue litmus turns red in the acid solution. That's what this picture shows. And here are some common acids and bases. So you can see here aspirin, that's acetylsalicylic acid. And you have the food, most food is acidic. Vitamin C is ascorbic acid, it's anti-scurvy acid. And vinegar there, acetic acid. Bases here, you have ammonia, baking soda, which is sodium bicarbonate. You have antacids there, looks like magnesium hydroxide, and you have drain cleaner. It's usually sodium hydroxide base. So those are all very strong bases. And then you have salt. So different salts. You have Epsom salts, aluminum sulfate, and sodium chloride, plain old sodium chloride salts. So these have neither properties of acids nor bases, these salts here. Okay, so here are some common salts, or I'm sorry, common acids. Sulfuric acid, this is also known as battery acid. The biggest thing that we use for acids and bases is fertilizer. So if you look at us as humans, like what do we manufacture? What are the things we manufacture the most of? And what we manufacture the most of is probably not surprising, is transportation fuel. So we make a lot of fuel. What is the second most thing we make? And that is fertilizer. So, and much of acids and bases, so much of sulfuric acid, much of nitric acid, we don't have nitric acid on this list, and ammonia is on the base list. We use those to make fertilizers. And on the order of about 75% to two-thirds of acids and bases made are for fertilizers. So hydrochloric acid, this is also known as muriatic acid, and it can be used as a cleaner. So you also use it in pools. So swimming pools, you can put hydrochloric acid in. And sulfuric acid, hydrochloric acid, they're very strong acids. They're strong electrolytes. You remember that from last chapter, where they make a strong, in solution, they conduct make water conduct electricity well. Phosphoric acid, used in cooling. Also used in as a fertilizer. We tend to use just plain old phosphate, like or phosphorus oxides, as fertilizer as well. That you make phosphoric acid from them. Lactic acid, we make this in our muscles as well. And it's used in yogurt. Yogurt in our body makes it in fermentation process. Acetic acid, this is vinegar. These are weak acids. Boric acid, we can use this to clean. Boric acid is great to killing ants and roaches. I like using boric acid because, well, I guess it depends. You can take boric acid as a powder, and you can put it on like around your house, something like that, and then that can kill insects because, well, insects, they groom themselves frequently, and boric acid is just, it's really it scratches them. So if ants walk over some boric acid, for instance, and when they clean themselves, they end up scratching themselves with the boric acid crystals, and then it'll slowly kill them that way. So and also boric acid, also sodium borate or borax. Uh, Ants can take that back to their nest, and they can feed each other, and then the borax will kill all the ants that way. So it's whereas, and this is compared to mammals. So I washed my hands with borax. So I use, like, if I work on my car and I've got really dirty hands, I'll wash my hands with borax, and it's because of the grit in them. It's really good. It takes everything out. So it's, and you can eat it if you want, but I mean, it doesn't taste very good. But you can eat it, and it's not going to hurt you. Whereas ants, it kills very high. So that's to me, I like this as a pesticide because it's completely harmless to me. And then hydrocyanic acid, cyanide, use it to make plastic, specifically acrylonitrile. That's the what they make a lot of yarns and carpets out of. It's a very weak acid, and of course you can see HCN cyanide. It can kill you. It's very toxic. So, oh, and I didn't talk about acids, the Arrhenius theory. So, let's talk about the different theories. Arrhenius theory: if you throw an acid into water, it forms hydrogen ions. For a base, if you throw it in water, it forms hydroxide ion. That's the Arrhenius theory of acids and bases. Here are some common bases. Sodium hydroxide, this is also known as lye. So LYE, lye. You can use it in soap making, is a very common thing. So if you've seen the movie Fight Club or read the book is hilarious, by the way. If you get a chance to read the book, I highly recommend it. I laughed through the whole thing. But soap making, the way you make soap is you take fat, any fat, and a fat is a triglyceride. You'll learn about this more later. But what the sodium hydroxide does, it breaks the glyceride bonds and pops out glycerin, and then the sodium salt of the surfactant, and we call that soap. So potassium hydroxide here, this can be used for making liquid soap. So Castile soap, for instance, is typically potassium hydroxide, and biodiesel. So biodiesel, we'll talk about it more about this organic chemistry. It is an ester, biodiesel fuel. You can, if you mix a vegetable oil with ethanol or methanol, and then mix it with potassium hydroxide. You can do it with sodium hydroxide too, and agitate it and heat it up. You will make biodiesel. Lithium hydroxide is another strong base. We can use this for alkaline batteries. Alkaline means basic. Calcium hydroxide. So this is how you make plaster. And I took a class in metal casting, and we would do what's called an investment in plaster. And this is a lot of fun. You take calcium hydroxide and this is cement. I guess I'm thinking of magnesium sulfate. That's the other plaster. Sorry about that. Magnesium sulfate is another plaster we use. But calcium hydroxide, this is used to make cement. The calcium hydroxide reacts with air, carbon dioxide and air, to form calcium carbonate. And if you notice here, calcium hydroxide is a strong acid, and you got to be careful with that. So that's why they tend to yell at people for putting their fingerprints and whatnot and carving initials in lime and the cement, because if you rub your eyes, it can damage your eyes, it can damage your skin too. And calcium hydroxide, also I said lime, can be used to sweeten the soil, makes the soil more alkaline, more basic. So I mentioned magnesium. Well, the calcium sulfate. That's another plaster. That works by you mix it with water and it forms a magnesium sulfate hydrate. Okay, going on the magnesium hydroxide. This is used as an antacid. And ammonia, it's a weak base, and its primary use is fertilizer. So, and to talk about this being made in the United States, most of the ammonia is made in Russia. Actually, we make a lot of sulfuric acid here in the United States, but Russia makes most of the world's ammonia. Okay, so acids base. When an acid reacts with a base, it forms water plus a salt. I mentioned that there, the salt no longer has the properties of the acid or the base. And here's Arrhenius theory, and there's some limits. So, and this is something, so hydrogen ions not necessarily exist in the water solution. This is not necessarily true. The truth of the matter is we honestly don't know. We think that they actually they exist as hydronium ions, H3O plus. And the reason why we know this is by computer simulation. But we know that H3O plus does exist in solution because we can do spectroscopy on it. We look on the electrons. The thing is H plus is a proton. It has no electrons. So we really don't know how to probe the H plus by itself, and there's not enough of an influence for the nucleus to be changed really. So on this one here, this first point, this is something that we honestly don't know, but we kind of say it's true. I mean, there is some proof because it's computer simulations, but simulations are not real data. So this is not experimentally verified. So which makes it not a true fact in contemporary science. Arrhenius theory, it doesn't explain why ammonia is basic, and it only applies to aqueous solutions. So although ammonia, it partially explains if you throw ammonia into water, it does form hydroxide ions. Okay, so the better theory is the Bronsted-Lowry theory, where an acid is a proton donor and a base is a proton acceptor. So if you see here, HCl gives a proton to H2O water. So water gains a proton, HCl loses a proton, and that makes HCl an acid and makes water a base. Now you look at the next equation, you have ammonia, NH3, and H2O water. Ammonia, NH3, gains a proton, so that makes it a base, and water loses a proton, that makes it an acid. So now you're like, wait a second, now you have water is a base in the top equation and water is an acid in the bottom equation. Come on, water, what are you doing? You're going both ways. What's up? Water is a substance that is called amphoteric. It is both an acid and a base. So there are other amphoteric compounds, amino acids that make up proteins. Those are all amphoteric, for instance. But water is special. Water is a very weird compound, and there are many things that are strange about water. One of them is the fact that it's amphoteric, which is uncommon. Okay, and here's illustrating the acid and the base. The acid is the proton donor, the base is the proton acceptor. So it's like acid is the pitcher, base is the catcher. If you're, instead of a hydrogen, if you think of a baseball. Okay, so now let's talk about some salts. So ionic compounds, salts, they're no longer acids or bases. So here we have silver nitrate. So here's some common acids and bases. Silver nitrate, this is used as a antiseptic. So they still do this. They sell Band-Aids with the silver nitrate in them. And caution, I'm very white. I'm a Caucasian, and if you put silver nitrate on a Caucasian, it'll turn his or her skin brown. So if you start playing with silver nitrate and your skin turns brown, don't freak out. That's completely normal. Tin fluoride. This is used as a toothpaste to get rid of cavities. What the fluoride does is it decreases the solubility of the mineral that's in teeth. It's called hydroxyapatite. So it replaces the hydroxides and hydroxyapatite with fluoride, and it makes the tooth enamel harder and less soluble. It also tends to kill the bacteria. So it's more or less a triple whammy, if you will. It's better. Its primary is to make the teeth harder and less soluble. Sodium fluoride can also be used for that. Calcium sulfate. This is what I mentioned there. We use it in my art class. Plaster cast. Of course, we tend to use fiberglass now, or those braces or air casts are much more common nowadays. Epsom salts. So magnesium sulfate septohydrate. So this is a laxative. So basically, all magnesium stuff is a laxative. That means it makes you go to the bathroom more readily. You can use it to soak your feet as well. So if you ever get calluses or your feet are really sore, you can soak them in Epsom salts. And if you want to get rid of calluses, you can soak them in Epsom salts and then scrub them with an emery board, and you can get rid of the skin that way. Potassium permanganate. This is purple stuff. It's kind of cool. If you have the crystal and you throw it on wood, it actually can catch the wood on fire. It's very reactive. But it can be used to it's used to treat really severe cases of athletes' feet. So like the trench foot that the people had to deal with in World War One. Many times potassium permanganate was used. Iron 2 sulfate. This is used for iron deficiency. Even better for iron deficiency is actually chelated iron. But iron 2 sulfate is the standard for that. Zinc sulfate can be used to treat eczema. Barium sulfate, this is a contrasting agent. And I can tell you this stuff tastes terrible. I had to get that. I had a CT scan of my gut done once, and I did the barium sulfate drink plus the iodine injection. And man, that barium sulfate, they try to flavor it, but it still tastes terrible. And mercury chloride, yeah, we don't use this anymore. This is please don't take this stuff. This is bad. So, all right. And moving on, talking about more things. Anhydride means without water. So, if you have an anhydride and mixed with water, you form the acid. So, SO3, sulfur trioxide, is the anhydride of sulfuric acid. So the battery acid, very strong acid. And you can even further, you can have something called fuming sulfuric acid. You can get sulfuric acid and then mix more SO3 gas to dissolve in there, and that's even stronger acid that way. And metal oxides, these are basic anhydrides. So basic mean alkaline, so pH greater than 7. So calcium oxide lime reacts with water to form calcium hydroxide. So maybe you've heard of the limelight before. So I hear that in some like contemporary songs. Hey, she's addicted to the limelight. Where did that term come from? The limelight. Limelight came from the fact that you can make a spotlight by taking lime, and if you heat it, it starts to glow. And then, so heating up with just a torch and some lime and a mirror, that's how you made a spotlight back in the olden days. That's where the limelight came from. So, for whatever reason, we've still used limelight, in contemporary in references. Good old-fashioned chemistry making its way into society. Okay, so strong and weak acids and bases. So strong acids are strong electrolytes. Weak acids are weak electrolytes. So Strong acids, they they're like you ever go to a party with someone and a strong acid is like it's like an Uber pool or something like that. You if let's say you have a group of people that you don't really like or hang out with, and you're in a car, and then you get to the party. What happens? You just leave each other. Like, all right, we're here, bye, and you just go your own separate ways. A weak acid, a weak acid is like a really disgusting couple in love. Okay, a weak acid prefers to stay together. So if you go to a party and you see a really cute couple in love, they're what? They're hanging out, they're holding hands, and they're really next to each other. When do they separate? Like to go to the bathroom. Like maybe one will wait outside the door while one is in the bathroom, kind of thing. And but rarely do you see them apart. So that's the same idea with weak acids. They will occasionally iodize, but only ever so slightly, whereas strong acids and bases are like, "Beep, see you later, suckers." Same thing. Same thing with strong bases. Same as strong acids and weak acids. Strong bases completely ionize. Weak bases tend to like to hang out together. And here's ammonia. And we already mentioned this, that ammonia is a proton acceptor. Make by Arrhenius theory. Then neutralization. So the process by which an acid or base is no longer is neutralized, taken care of, loses its property is called neutralization. And what happens after neutralization? It forms water. So generally speaking, acids add positive charge and bases add negative charge. And then when they're neutralized, they come together and neutral water is formed. So forms the acid and the base combine, and it forms a salt and water. So sodium hydroxide, Li, is a very strong base. I do not recommend you taste it. I've never tasted it, and nor do I want to. And I imagine it would hurt. You would get blisters on your tongue. Hydrochloric acid is an acid. It's a stomach acid. So I'm sure everyone at his or her point in life has thrown up and tasted the acid from your stomach, and it burns and it hurts. So, and it's really, really sour. And because it's a very strong acid. And how does salt taste? Does it taste really bitter? And does it taste sour? No, it tastes salty. It's something new. And I should mention that the bitter flavor, it tastes like really cheap medicine. Like if you have cheap medicine, like if you buy the off-brand of some medicine, like a cough syrup, and you have that flavor, and you're like, what is this stuff? That's the bitter flavor. It's not bitter melon, although I don't like the taste of bitter melon. But like I mentioned, bitter melon is in fact acidic. But bitter is by instinct. Humans do not like it. Okay, so, and this is phenolphthalein. This is an indicator. And as you are titrating, which you may do if you take a lab, we won't do this in the lab kits, but if you take a lab face-to-face, you will undoubtedly use phenolphthalein at one point in time. It turns pink when it's alkaline, and it's clear when it's acidic. And here is the pH scale. The pH scale is the power of hydrogen. So if you have, it's the minus log of the hydrogen ion concentration. What does this mean? It means for every step in pH, the concentration changes by a factor of 10. So neutral water has a pH of 7, and then less than 7 is acidic, greater than 7 is basic. And that's supposed to be at 25 degrees Celsius. But if you look at here, so neutral is at 7, and water is pH of 7. The truth of the matter is there is no such thing as pure water here on Earth, because water will absorb carbon dioxide and become acidic. And you can see here basically all food is acidic, although I guess it depends if you think blood is food or not. Blood has a pH of about 7.4. Then baking soda, seawater has a pH of 8.5-ish, so seawater is slightly alkaline, and so on. And but most food and urine should be acidic. So I already mentioned this power of hydrogen. Each pH step is actually a step in 10 for concentration. And here are some approximate pH values of some common solutions. So hydrochloric acid, your stomach acid. So this is not entirely true. Your stomach is not always this low of a pH. So typically at rest, your stomach may have a pH of like 4 or 5 in that range. But after you eat something, then the stomach will release acid, and then the pH will drop. So you can see here soft drink, lemon juice, these types of things. So and rainwater. Rainwater has a pH of 5.6. That's saturated with carbon dioxide. And if rainwater has a pH lower than 5.6, that is known as acid rain. We'll talk about that later. And see the other things here. What is that? And I said most foods. You can see there are a few. Egg whites are a little alkaline side, but it's more the exception to the rule than the rule itself. And so on. So those are here is some common things with the pH scale. And let's talk about properties of acids and bases. So conjugate acid and base pair. So an acid will form its conjugate base. So some reactions go forward and backwards. So the conjugate base, this is easy to explain when I have a chemical equation. But the forward step is going to be an acid, and the backward step is going to be its conjugate base. And a base, the forward step is a base, the backward step is its conjugate acid. And we have a special type of solution called a buffer. A buffer is something that reduces the change in pH. Fairly commonly, a weak acid is conjugate base. You can have a weak base and it's conjugate acid, but it's more often the weak acid is conjugate base. So, I already mentioned this, acid rain, pH less than 5.6, and that's from other pollutants like sulfur oxide, and nitrogen oxide. So, okay, and acids. So, antacids. Hyperacidity is when your stomach makes too much acid, and you can get rid of this by eating antacids. So, a problem with just continually eating antacids, you can get an increase in blood pH. This is known as alkalosis. Although alkalosis, unless it's from ingestion of huge amounts of things, tend not to be too serious. Easiest cure for alkalosis is have someone hold his or her breath. Okay, antacids. So having the remedy here. These all get rid of. Just directly react with the acid to get rid of them. There's a couple ways to get rid of acid in the stomach. This one is a direct, the acid is consumed. So here are the common ones. So calcium carbonate. Most common ones are calcium carbonate and magnesium hydroxide. Rolaids is magnesium hydroxide. Tums is calcium carbonate. You tend not to use these other ones. Well, baking soda is not used as much anymore because of the sodium in it. You can also use other types of things. So Nexium is a proton pump inhibitor. So what Nexium does is it shuts down the proton pumps. The way that your stomach makes hydrochloric acid is that it takes a proton from water in your bloodstream and transports it across what's called the proton pump, and then it deposits it into your stomach. And the proton pump inhibitors, they shut down those processes. So Zantac here is known as an H2 blocker. So H1 block, it's a histamine response. So what is a histamine? Histamine, first of all, it's an amine, which means it has a nitrogen in it. We'll learn more about that in organic chemistry. But let's say you're probably more familiar with the H1 process. So if you um, let's say I'm allergic to mold, for instance. If I go into a room that has a lot of mold, then I get kind of itchy, kind of thing, and I might cough a little bit, and that is my body's H1, or it's the H1 response. It has a histamine response to that, and when you're it's part of your immune system. So when your body finds something foreign and like, what is this? I don't like it. It will release what are called histamines, and then that starts your body's immune response to that. H1 blockers are things like Claritin or Benadryl. They stop that way. H2 blockers work. They're a histamine response, and it works though in your stomach. It's kind of like if maybe I'm showing my nerdy wings here. It's like the Jedi mind trick. It's if you take an H2 blocker, it's like the Jedi mind trick. There is no need to make more acid. Like, these are not the droids you're looking for. You do not need to make more acid, stomach, and your stomach will not make as much acid if you take the H2 blockers. So you have three ways to get rid of acid. You can directly neutralize it with antacids. You can take the proton pump inhibitors, or you can take the H2 blockers, where it just tells your stomach just to not make any more acid with the chemistry version of a Jedi mind trick. So the most effective of all those are the proton pump inhibitors. Those shut down very strongly. Proton pump inhibitors are, at least as far as long term, that's the best for getting rid of stomach acid. And I mentioned this last chapter that we make. This is not true though. That it's not leading chemical substance produced in the United States. It is. What's produced more is transportation fuel. But if you discount transportation fuel, this is true. And of this, we use it to make fertilizers. So hydrochloric acid, and we use it for various things, but mostly for cleaning and etching of metal, that kind of stuff. And we make 4 billion there. So lime, how we make lime is we take in limestone and we heat it up. And the people that figured this out are the Romans. So the Romans, they would take lime and they would heat up limestone to make lime, and then they would mix it with things and to make cement. So Romans also invented cement, and then they put that between their rocks and their arches and whatnot to build things. And and we can also use it to sweeten soil. So this shows here. Why do you sweeten the soil? Because most fertilizers are acidic. I guess you can have some basic ones, but they tend to be volatile, so they just fly right away. So lime is used to sweeten the soil to change the pH balance of the soil because of all the chemical fertilizers are added. Sodium hydroxide, also known as a lye, used as a cleaner. It's most usually to make soap. So be very careful with oven cleaners and also drain cleaners. Those are very caustic. Base burns tend to be worse than acid burns. And do not get this stuff in your eyes. That will blind you very quickly. Ammonia. Thing is that we don't really make that much ammonia in the United States. Most of the ammonia is made in Russia. So we import a lot of our ammonia from Russia because ammonium sulfate. So that's one of the most common fertilizers, and nitrogen ammonium nitrate. So it's 2 parts. So ammonium sulfate is 2 parts ammonia to 1 part sulfuric acid, and ammonium nitrate 1 part ammonia to 1 part nitrate, and you make nitrate from ammonia as well. So, if you're wondering where the disparity is, so the sulfuric acid is here. You have 40 billion kilograms, and then you only have 11 billion kilograms of ammonia, Where's the discrepancy? It's because it's really most of it's made in Russia, and we import it. So, and in general, concentrated acids and bases, they are corrosive and they have a human health hazard. What's the health hazard in strong acids and bases? They denature the proteins. We haven't talked about biochemistry yet, but a protein's function is all about its shape. And denature protein means it changes its shape. Once the shape changes, it doesn't work anymore. So, luckily, though, we are covered with a very thick layer of a protein called keratin, which is made up of our hair, skin, and fingernails. So, the outside of our bodies tend to be much more robust than the inside of our bodies. So, with a few exceptions, like the stomach lining. Your eyes, unfortunately, do not have a layer of keratin, thick layer or layers of keratin around it. So, get acids and bases in your eyes, it will damage it right away. So keep that in mind when working things. I always wear safety glasses. I'm sure my neighbors think I'm crazy because even when I work on my car, when I work in the lawn, I have either sunglasses on or I have my lab safety glasses on. And we have our body, the blood has a pH buffer in it. So it's hard for the blood's pH to rise and fall suddenly because we keep our blood buffered, and that protects our organs from failing. But frequently, though, if a patient crashes, it's typically one of the either directly caused or causes the blood's pH to change. And when the blood's pH change, that's when systems start to fail and you have organ failure, and then death usually follows there soon thereafter. So, but we do have the buffer. We actually use baking soda. Our body uses baking soda. And it's nice because that's also, we take a waste product, carbon dioxide, and we use it to regulate the pH of our body. And that is it for this chapter. So I will see you next class.